Good morning, students. I am Dr. S.P. Yadav, Professor and Head of Electronics and Communication Engineering Department in Guru Nanak Institute of Technology. We are now learning analog and digital communication in this semester. So, in continuing to that, now we will be discussing today Unit 4, Pulse Modulation. So, first of all, we have learned in Unit 1 and Unit 2 amplitude modulation and frequency and phase modulation. These were the continuous type of modulation techniques. Now we will be discussing pulse modulation, which is a transition between analog modulation and digital modulation. So let us say this is your analog modulation, and this is the digital modulation. Digital modulation. So in between analog and digital modulation, there is a transition which is called pulse modulation. So pulse modulation is nothing but a transition between analog to digital modulation. Pulse modulation is a transition from analog to digital modulation. As we know that there is a continuous time signal. So this is a continuous modulation technique. This is here is a discrete digital signals 0, 1, 1, 0, 1, 1, etc. So in between digital and discrete, analog and digital, we have discrete signals. Okay? Discrete signals like this, discrete signals. This is amplitude, this is time. So this is similar to that. But before going to the chapter, we should know what is modulation. Just we have already discussed, learned in Unit 1 and Unit 2. Just anyone repeat what is modulation? If not, then I will tell. Modulation is a process in which a low frequency message signal is superimposed upon a high frequency carrier signal in such a way that some characteristics of the carrier signal is varied according to the low frequency message signal. So in amplitude analog modulation, we have already discussed three different types of modulation, that is amplitude modulation, phase modulation and frequency modulation. So in amplitude modulation, amplitude of the carrier is changed according to the message signal. In phase modulation, phase of the carrier is changed according to the message signal. Similarly, in frequency modulation, frequency of the carrier is changed as per the message signal. Similarly, here in pulse modulation, instead of just you see continuous time signal, what is that signal and message? So in continuous time signal, let us say this is the message. This is the message which is continuous. This is GT message, continuous, and we are using a carrier which is also continuous, okay? And then we get, as per the type of modulation technique, some change in the carrier signal. For example, if we are using a frequency modulated signal, then we have what? Frequency changing as per the message signal. So this is the points where frequency will be varying. So during this is positive, so frequency will be more, this is negative, so this will be frequency will be less during this time. Again next cycle it will be more, next cycle it will be more, okay? So this is a continuous time signal. From in pulse modulation, what is the difference between analog modulation and pulse modulation? In pulse modulation, message is your analog signal only, continuous time signal only, but this carrier is not continuous. It is a form of pulse train. So if I write for pulse modulation, so this is your message signal. Let us say this is GT only, but this carrier is now, this is carrier. So and this is message, and this is modulated signal. I will write FM, frequency modulated signal. So here this carrier is not continuous, it is a train of pulses, that is called pulse train. So we are having this type of pulse train. So this is the basic difference between analog modulation and pulse modulation. Okay? Here carrier is not a continuous time signal, it is a discrete signal which is in form of pulse trains. So if I write this, this is nothing but delta, or we can write PT also, P for P, this N minus TS, where T is the time period between these two. This is the T, time period between the pulses. Okay? Or you can write delta also if we take impulse function, but normally we take pulse function. Okay? So then we get, as per the modulation technique, suppose we are going to do pulse amplitude modulation. So here amplitude of the pulse train will vary as per the message signal. So if I have to write what is the modulated signal in pulse amplitude modulation, so you just take here pulse amplitude is varying as per the message signal. Pulse amplitude is varying as per the message signal. So this is the basic difference. If we talk about discrete digital modulation techniques, so here we convert this not into discrete form. Here it is in discrete. This is carrier is in discrete form. Here we convert into digital form by quantization. So that we will discuss in unit 5, but unit 4 we will more focus on pulse modulation techniques only. So what is the difference between analog modulation and pulse modulation? Carrier is in discrete form, which is in the form of pulse trains. Okay? So here if we want to write what is the modulated signal, so modulated signal is nothing but let us say I am writing GNTS. So this is nothing but a sum of weighted function, which is your GT and delta N minus TS. This is the equation for this pulse amplitude signal, where this is the mass function because its amplitude is 1, always 1. Okay? So this is the basic difference. It is pulse modulation is a transition between analog modulation to digital modulation techniques. Okay? But we must know, or already you have studied this in signal and system in semester 2-1 sampling theorem. Once I will revise sampling theorem, because we need a pulse train which should be discrete in nature, which is obtained by sampling of a continuous time signal using Nyquist criteria. So first, shall we revise sampling theorem? Can anybody tell what is sampling? एक बार उधर. Oh, sampling, because in pulse modulation we are using, instead of a continuous time signal, a pulse train, or impulse train. So sampling, it was given by Nyquist. There were two scientists in the field of communication which revolutionized the communication system, and because of that we are seeing the modern communication system which has got very high transmission rate, very less bit error rate, and much more things. One among them was Nyquist. Nyquist told that if a signal is continuous, we can make it discrete. By using certain rule. We can make it discrete. So he showed a path that continuous time signals need not to be required to be used. You can make it a discrete one. So Nyquist was the first one. I will tell what is the Nyquist theorem. Another person in the communication field of communication history was Shannon. So Shannon gave maximum transmission capacity theorem. He told that the channel capacity can be B is the bandwidth log to the base 2 1 plus signal to noise ratio. So we can increase the channel capacity and hence we can get more transmission rate. Okay? Earlier we were transmitting in kbps, kilobits per second. Now in fifth generation or even in sixth generation, we will be talking about gigabits per second, not kilobits per second. So because of this, he told the maximum channel capacity is bandwidth into log to the base to 1 plus signal to noise ratio. So if we increase signal to noise ratio, means reduce noise, or we increase bandwidth, we can have maximum more channel capacity. And for distortion less transmission, the channel capacity should be less than or equal to the rate of transmission C. This is also a Shannon theorem. Okay? So if we want to increase the speed of transmission, we have to increase either bandwidth and or signal to noise ratio. But there is a trade-off between signal to noise ratio and bandwidth. If you increase bandwidth, signal to noise ratio will reduce. It is bandwidth is similar to, just consider a winter season. So winter season, lot of cold waves are there outside. If you open the doors and windows, cold waves will come. So if you consider cold waves as noise, then you will get more cold. Okay? So you are allowing more noise to come. Windows, your doors are a way to allow noise to come. So if bandwidth is more, signal to noise ratio will reduce. If signal to noise ratio to be kept high, then bandwidth has to be low. As it is in winter season, you have to close all windows and doors so that you do not allow cold waves to come inside the room. Okay? So there has to be a trade-off between how much bandwidth to be allowed, how much signal to noise ratio to be allowed. So these two persons were very important in the field of digital communication. They showed the path, Nyquist showed the path, need not to use analog signal. We can make it discrete. And even we can make digital also by quantization and encoding. Okay? Shannon told that we can increase the transmission rate by following this formula. Now there is a debate. I have already read some papers in IEEE. I attended conference also, and we discussed also. In 6G, we are going to break this barrier of channel capacity. You can transmit more than the channel capacity of a given channel. Already we are doing in 3G, 4G, MIMO technique. So MIMO technique, what is that? Multiple inputs, multiple outputs. So you are at a time using several channels. So hence the rate of transmission is increased. In 5G, we are using massive MIMO. So that has again further increased. 6G, this barrier will be broken. Up to 5G, the Shannon capacity theorem is followed. But it is expected that we will break this barrier and we can transmit, even massive MIMO is not required. We can transmit more than the Shannon given by the channel capacity given by the Shannon theorem. Okay? But it is still research is going on, and lot of things has to come to prove and verify this. Okay? So now let us talk. What is Nyquist theorem? Nyquist theorem says, for a band limited signal which is having finite energy, if the signal frequency, message signal frequency is maximum signal frequency is FM, then if in order to recover the signal, we have to sample the continuous time signal by twice that of the highest frequency present in the message signals. So there are 3-4 conditions. One is the signal should be band limited. Signal should be band limited, and in order to make it band limited, we use a low pass filter so that we receive only the wanted band of the signal, not unwanted. First condition is this. Second condition is it should have finite energy. One more condition is, but that is not that much valid. The signal should be real valued signal. Okay? Signal. So if these things are there, and if the highest frequency of the message signal is, let us say message signal highest frequency, message signal highest frequency is FM, then we can sample the signal. If the sampling rate is, the sampling rate Fs is greater than 2 into Fm, then we can recover the original signal from the sampled value of signals, okay, from the discrete signal. I will discuss 3 different conditions later on, but let me first emphasize what is maximum signal. Suppose a music concert is going on. So there will be different instruments being played. There will be tabla, there will be harmonium, there will be some lady singer, there will be some gent singer. Different instruments will produce different frequencies. Okay. So while sampling, we have to consider the highest frequency component available in that composite signal. Just I will give one example. Let us say one signal xt is given by 4 cos 2 pi 100t plus 3 cos 2 pi 1k t, that is 10 to the power 3t. So in which, what is the maximum frequency available? What is the maximum? Sampling should be done at what rate? Fs should be greater than or equal to 2 Fm. What Fm you should consider? F1 is 100 Hertz. Let us say 100 Hertz. This is 100 Hertz. F2 is here. F2 is 1 kilohertz or 1000 Hertz. Which frequency you should consider for sampling? Highest frequency component. Otherwise, you will land into aliasing problem. So you should consider this frequency highest frequency. That is why this message signal we should consider the highest frequency component available in the composite signal. Highest frequency component. Okay. So in this case, if we have to sample, then sampling frequency should be greater than or equal to 2000 Hertz. Okay. This is one example. Understood now? So this is why we are discussing sampling, because we will be using samples or train of pulses for making pulse trains, okay, of the modulated signals. So you have understood what is sampling. Sampling is a process of making a continuous time signal into discrete time signal following this Nyquist criteria. This is sampling theorem also it is called, and it is called Nyquist criteria also. What is this? For a band limited signal having finite energy and the signal should be a real valued signal, then we can sample the signal at a rate which is greater than 2 into the maximum value of the signal frequency of the signal available in the message, okay, in order to recover the original signal. But once we sample it, we can never get exact replica or exact original signal. We are going to lose certain information. Okay. That is another thing. But before that, you see 3 different conditions. If we do sampling at less than sampling rate or greater than sampling rate or as equal to Nyquist criteria, what will be happening? So just take 3 different conditions. 3 different conditions. One is if sampling rate Fs is less than 2 into Fm, then what will happen? Anybody can tell? If sampling rate is less than 2 into, aliasing effect will occur. So, dekho, one signal I will write here only so that we will cover. One signal is this, another signal is this, another signal is this, another signal is this, another signal is this. So here what we are seeing, this, there is a cross of one signal in other signal. This is called interference in terms of communication system, and in signal and system or digital signal processing we tell aliasing. So this is the aliasing which is occurring. This is called aliasing. So we should never sample a signal less than 2 into Fm. This is unavoidable. Second case is Fs is greater than is equal to 2 into Fm. So this is called sampling at Nyquist rate. Is it okay or no? Can we do sampling at Nyquist rate? Tell yes or no. Tell loudly. So I will give example. This is one signal. This is another signal. This is third signal. Let us say this is fourth signal. If we are doing sampling at Nyquist rate, this is the condition. Okay. Theoretically it is okay, but practically it is not okay. In word, none of the devices are ideal in nature. How we are doing band limiting of signal? By passing through a filter. Let us say low pass filter. Okay. So you should have a sharp cutoff frequency in order to avoid aliasing or in order to avoid interference. Okay. So, but देखो ideal case I will draw a low pass filter. So this is the low pass filter response. This is a pass band, and this is a stop band. Okay. This is frequency, and let us say F1 is the cutoff frequency. This is 0, and this is maximum amplitude. Let us say A. Okay. So this is the response of a low pass, ideal low pass filter. This is ideal low pass filter. But as I said, none of the device in the world is behaving in ideal way. What will be the practical response of the low pass filter? It will be like this. This is your stop band. This is your pass band in ideal. So practical, you see, practical, if I take this as a reference point, so देखो, here this amplitude is constant. Hello, just listen, see here. In practical low pass filter, let us say this is your A. So this amplitude is constant at A, but in practical low pass filter it will not be constant. So it will have ripples. It will be changing. Now here it may, if you observe the Gibbs phenomena, it can go overshoot also. Then if you don't consider this as a rectangular pulse pass signal, then it will come here and it will come like this, and then again it will pulsate and die down. So for dying down, it will take certain time. So here pass band, a stop band. This is pass band. This is a stop band, and this is unwanted band which is observed in any practical filter, that is called transition band. So you will not get a sharp cutoff filter, okay, which will have cut this signal at this point. Okay. So actually it will go somewhere else. So practically what will happen? This signal will go here, this signal will go here, and again there will be interference. There again will be aliasing. समझ में आया ना? So because this is transition band, which is not present in ideal filters, and when we are considering theoretically, then we are considering ideal filters only. Analogy you have, suppose you are riding a bicycle or motorcycle. Somebody comes suddenly in front of you, you apply brake. Motorcycle will not stop suddenly because of its momentum, because of the moment of inertia, it will go somewhat ahead and then stop. So similar is the practical case. It will not go suddenly down, it will take certain time to settle down. Okay. So, and this is constant amplitude. Here there is no constant amplitude, there are ripples. Here also this is constant 0. Here it is not 0, it is 10 dB. Here it is, let us say this is your 70 volt. If this is 100 volt, so 70 volt permitted, 3 dB. Okay. And here minus 1 dB, up to 10 volt is permitted. 10 volt is considered as low voltage or no voltage. Okay. So you should not do sampling at the rate of Nyquist rate. Okay. Because none of the devices are ideal in nature, and you will get aliasing or interference because of the non-ideal characteristics of the devices. Okay. So what is the best way? Best way is you should what? You should always sample at what rate? Fs should be greater than 2 into Fm. What should be the greatest value practically? If you go 8 times, 8 Fm better, 10 Fm better, more you go, it is better. But what there will be some problem, I will discuss. So if we are sampling greater than the Nyquist rate, what will be the response? Dekho, this is one signal, this is another signal, this is another signal, third signal, and there is a gap. There is a gap, just like divider on your road, which will avoid interference. So always we should do sampling at greater than the Nyquist rate. If you do sampling at much higher rate, as I discussed in the previous class, if you do sampling at much higher rate, there will be a problem. What is that problem? Yesterday we discussed image formation. So if the sampling rate is very, very high, then we will have images in the receiver. Okay? And in order to nullify the effect of image, what we should do? We should use a filter which should have high quality or low quality. Quality factor should be high or low? High. Quality factor should be high. So we have to use anti-imaging filter, which will filter out the images which are formed because of the high rate of this sampling. Recently I published one paper presented in Mahindra University. My paper was titled on multi-rate sampling for our 5G or 6G communication system. So if we do low sampling rate, we will get what problem? We will get aliasing. If it is low, then we will get aliasing. And if it is high, we will get imaging. So because we need different sampling rate for different signals, different communication system, so you can go for low rate of sampling also, even below the Nyquist rate, but there you have to use anti-aliasing filters in order to remove the aliasing effect. And if you are going for a high sampling rate, then you should do anti-imaging filter. In normal case, you should consider always sampling rate should be greater than twice of the highest frequency component available in the composite signal. Okay? So that is the sampling theorem in short, brief. Now again we will come back to pulse modulation because this is our topic. Modulation, because we diverted our topic to sampling, because we wanted to revise what is sampling theorem, because we will use a train of pulses which are discrete in nature as a carrier signal in pulse modulation. One more thing I want to discuss, pulse modulation is called a baseband modulation. Baseband modulation technique. Okay? Whereas this AM analog signal modulations are called pass band modulation. What is the basic difference between baseband modulation and pass band modulation? Even digital modulation techniques are baseband modulation techniques. In baseband modulation technique, the frequency is near to zero. It is low frequency. Let us say this is frequency. So here we are operating. This is amplitude versus frequency. So frequency is low, baseband modulation. In pass band modulation, the modulation frequency, carrier frequency is very away from the zero. Okay? So this is a pass band modulation. This is a break. So if I take carrier frequency at 10 megahertz, so this is your pass band modulation. If we take carrier frequency at let us say 1 megahertz or not 1 megahertz, 10 kilohertz or even 100 kilohertz. Okay? So this is your baseband modulation. Okay? Baseband modulation. The carrier frequency is much lower whereas in pass band the carrier frequency is much higher. So in digital modulation and pulse modulation, actually it is a technique of baseband modulation where we do modulation at low frequency level, but before transmission we once again do pass band modulation either AM or FM and then transmit the signal first. So this is the basic difference between pass band and baseband modulation. Now you see different types of pulse modulation. So basically we have two different types of pulse modulation. So you can write here analog pulse modulation, and digital pulse modulation. Digital pulse modulation. Two techniques mainly. In analog pulse modulation, it is again further divided into two parts. Pulse amplitude modulation, and then pulse time modulation. ठीक है. Again pulse time modulation is further divided into two parts. One is pulse width modulation, pulse width or duration modulation, and pulse position modulation. Pulse position modulation. ठीक है. So basically three parts, but these two are combined as pulse time modulation, as phase modulation and frequency modulation is combined as angle modulation. Similarly, in digital pulse modulation, we have different types of modulation techniques. So it starts with pulse code modulation, PCM, pulse code modulation, PCM. It is not paracetamol. What is that? It is paracetamol? No, pulse code modulation. This is the starting of digital, pure getting digital signal. Here this is discrete signal. It will convert into discrete. Okay? So this is a discrete process. That is why it is called analog pulse modulation. The modulated signals will be still in discrete. Here the modulated signal will be purely digital, which with respect to x-axis as well as y-axis, and this requires some further processing, that is quantization and encoding, and here we will get signals in terms of 0, 1, 0, 1. Here we will get signal in terms of some pulses which are continuous in nature for some time, mainly in the amplitude and discrete in time. So this is pulse code modulation. Then we have differential pulse code modulation. I will write in short DPCM, differential pulse code modulation. Then we have delta modulation, and then we have adaptive delta modulation, ADM. I will write ADM, and many more. So these are the two different categories of pulse modulation technique. One is analog pulse modulation, another one is digital pulse modulation. In analog pulse modulation, we have mainly two types: pulse amplitude modulation, pulse time modulation. Pulse time modulation is further divided into pulse width modulation or pulse duration modulation, and here this is pulse position modulation. Similarly, in digital pulse modulation, we have pulse code modulation, differential pulse code modulation, delta modulation, adaptive delta modulation, and many more, because each will give certain, some have some disadvantage, and that is why we use another one. Now coming to advantage, why we should use pulse modulation? What is the advantage? First advantage is it will have better signal to noise ratio compared to analog modulation techniques. Better signal to noise ratio. It will be less affected by noise, than continuous time modulation techniques. Another thing is the power level in this modulation techniques are low. So it is a low power level modulation techniques. As we have compared AM and FM. FM is low power level transmission technique, whereas AM is a high power transmission technique. So if you compare AM, FM and PM also, so this pulse modulation requires much less power than the continuous time modulation techniques. Now just What is pulse modulation? Pulse modulation is a technique in which a low frequency message signal, which is continuous in nature, is superimposed upon a high frequency pulse trains which are discrete in nature, and the characteristics of the pulse train is changed according to the message signal. So this is pulse modulation. If you come to pulse amplitude modulation, is it any doubt? You have any doubt, any question till now? Yes, you can ask any question. Then we will go to this individual modulation techniques. Yes, anybody is having any doubt? Please do ask. No. Okay, let us go to this analog pulse modulation one by one. So just I will remove this. Shall I remove? Okay. So now coming to uh, analog pulse modulation, in which we have pulse amplitude modulation. Okay. So pulse amplitude modulation. ठीक है. This is under analog pulse modulation. Analog pulse modulation technique. Can anybody tell? Because you have already performed practical definition of pulse, that pulse amplitude modulation. You have already done an experiment. Experiment number? PAM you have not done. Okay. देखो, in pulse amplitude modulation, we are taking a signal. Let us say this is your continuous time signal GT. ठीक है? Then we are taking in place of continuous carrier signals, high frequency signals, we are taking a pulse train. ठीक है? So if I write P as pulse, so this is nothing but P T minus NTS, where TS is nothing but the duration between two pulses, time duration. ठीक है? And if we take sampling, then 1 upon TS. ठीक है? So this is the message signal. This is your message signal. Message signal. This is your carrier signal, which is in the form of pulses, carrier signal. And when we modulate it, we get not continuous signal, but a discrete signal. And the amplitude of these pulses will depend upon the amplitude of the message signal. ठीक है? So if I take this envelope as the message signal, so we will have pulse trains. I will this is pulse amplitude modulated signal, PAM in short it is called. ठीक है? Pulse amplitude modulated signal, PAM modulated signal. If we want to write mathematically, so suppose we are writing G delta T is the PAM signal. So what will be the equation? It will be sum. Now it is not integration because it is discrete in nature. So sum of what? This your GT ठीक है, into P T minus NTS, ठीक है, and from n is equal to 0 to infinity. So this is the equation for pulse amplitude modulation technique. If we take it as a impulse function delta, then impulse function has amplitude always 1. So this is the mass function or weighting function, which will decide what will be the amplitude of the signal at particular point of time. ठीक है? So this is your pulse amplitude modulated signals. What is that pulse amplitude modulated signal? A low frequency continuous time signal is superimposed upon a high frequency pulse trains such that the amplitude of the pulse train varies as per the message signal. Is it clear or not? Somebody repeat. What is this one? You repeat. What is pulse amplitude modulation? Just now I told. Yes, repeat. Stand up. Tell something. What is pulse amplitude modulation? बोलो. Okay, better. So what is the circuit? What is the circuit for this? Normally we take this. We take this here. Okay, we take this here. This is GT, continuous time signal. Hello, this is continuous time signal, and here is a modulator. Here we give a pulse train. Okay, sample of pulse train, and when we combine here, we get a pulse amplitude modulated signal. So this will be the envelope. Envelope we follow the same as the message signal. Okay. So here may be a sampler, here may be a mixer. We will see in the next class the actual hardware circuits. Okay. Using either ICs or a normal transistor, how to generate pulse amplitude modulated signals. Do you have any doubt? No. So other, shall I stop? So other things we will discuss in the next class. Okay. In next class we will discuss another type of analog pulse modulation, that is pulse time modulation. So in pulse time modulation again we will discuss two types, pulse width modulation and pulse position modulation. In pulse width modulation, width of the pulse will vary. In pulse position modulation, position of the pulses will vary according to the message signal. Okay, thank you. Any question do you have? Any question anybody want to ask? Okay.